Block number 1, Stereochemistry and Bonding, Unit 3, Organometallic Compounds of Alkali and Alkaline Earth Metals. Content, Objectives, Introductions, 3.3 Organometallic Compound of Lithium and Sodium, 3.3.1 Synthesis of Organolithium and Organosodium Compound, 3.3.2 Structure and Property of Organolithium Compound, 3.3.3 Property and Uses of Organolithium. 3.4 Organometallic compound magnesium synthesis property and structure bonding and uses. 3.4.1 Synthesis of organomagnesium compound. 3.4.2 Structure and bonding. 3.4.3 Reactions uses of Grignard Reagent. 3.5 Summary. 3.7.1 Multiple choice question type. 3.7.2 Short answer type question. 3.7.3 Long answer type question. 3.6 Reference and further studies. 3.1 Objective of these units are to introduce you with synthesis, property, structure, bonding and uses of organometallic compound of alkali and alkaline earth metals. Each organometallic compound with its special reactivity, method of synthesis and uses has been described. This structural bonding relationship has also been provided subsequently. At the end of this unit, students will be able to understand their reactivity and structure along with their uses. 3.2 Introductions. This chapter provides an introduction to the large area of organometallic chemistry of alkali and alkali earth metal. In an organometallic compound, one or more metal carbon bonds are present. The stability, reactivity, and structural property of each compound depend on periodic properties of the respective metals. 3.3 Organometallic compound of lithium and sodium. 3.3.1 Synthesis of organolithium and organosodium compound. Organolithium's compounds having particular importance among the group 1 organometallics and may be synthesized by the treatment of an organic halides with lithium or by following the metallation reaction using N-butyl lithium in presence of hydrocarbon, example hexane, as a solvent. Alkyl halide in presence of lithium and THF give alkyl lithium and lithium halides. So here this second compound in which is alkene halide in presence of lithium and hexane at 50 degrees Celsius give lithium alkene and lithium chloride. Then here 2-bromoanisole in presence of lithium and THF give 2-lithium anisole and lithium bromide. Then here ethene 2-chloroethene in presence of lithium and THF give 2-lithium ethene and lithium chloride. Then here 2-bromo 3-methyl um, butene in presence of lithium and THF give 2-lithium 2-methyl butene and lithium bromide. Then here uh, propine in presence of buthium lithium THF give lithium propine plus butyl hydrogen. Organolithium can also remove halogen from alkyl and aryl halide proceeding through halogen metals exchange is depicted. Synthesis of organolithium compounds. Here bromo benzyl bromophenyl in presence of butyl lithium gives lithium phenyl plus butyl bromide. Organic compound having active hydrogen such as acetylic hydrogen form salt with alkali metals. 2 moles of uh, butene react with 2 moles of sodium to give 2 moles of um, alkyne minus Na plus H2. Then here cyclo 1 3 YNE NaH react with sodium hydride in presence of THF to give Na plus cyclopropyl plus H2. Synthesis of sodium salt of organic compound possesses active hydrogen. Organolithium's compounds are more stable than other heavier groups. Alkali metals organocompound. Sodium and potassium form paramagnetic organometallic compound with many aromatic compounds. This is because of oxidation of metal in presence of aromatic compound. 3.3.2 Structure and properties of organolithium compound. Alkyl lithium compounds are polymeric both in solid state and in solution. In a alkyl lithium tetramer, the lithium atom forms a tetrahedral unit in ether, while in case of alkyl lithium hexamer, the lithium atom defines an octahedron. Weiss et al. Show that in the structure of methyl lithium, the average lithium-lithium bond length is 261 picometer compared with 267 picometer in dilithium. It was also established that in the structure of hexalithium, hexacarbon core of lithium 6,6H11 6 C6H11 1 by 4 cyclohexyl 6 lithium bond distance lie in the range 295 to 298 picometer, while the other six bonds are significantly shorter, 238 to 241 picometer. The presence of such aggregate in the solution is determined by multinuclear NMR spectroscopy, as the organolithium compound contains a carbon-metal bond. The polarity of covalent bond between two different elements can be determined by electronegativity. Difference between them. More the electronegative an element, more it attracts electron density. By virtue of this, partial negative charge remain effective in more electronegative element, while partial positive charge remain in electropositive element. An organolithium compound difference in electronegativity is 1.5 depicted in figure 3.4. Depiction of organonegativity of carbon and lithiums. Molecular orbital energy level diagram depicted in figure 3.5 represent a carbon-lithium bond having electron density towards more electronegative carbon having less energy are in its atomic orbital. The carbon-lithium sigma bond is closer to energy of sp3 hybrid orbital of carbon, while sigma anti-bonding orbital is closer to 2s orbital of lithium. Sigma molecular orbital have two electrons, so lithium carbon. 4 electron sp3 1 electron sigma star molecular orbital. This orbital participate in CH carbon hydrogen bond formations. Molecular orbital of methyl lithium 3.3.3. Property and uses of organolithium. Organometallics are very reactive and need to be kept free from moisture. Organometallic act as a base and easily get protonated even in the air. Figure 3.6. Protonation of organolithium compound. Lithium methyl takes hydrogen to form methyl hydrogen and lithium plus. Organolithium compounds are of great importance as synthetic reagent. Alkyne and allyls organolithium are used to synthesize two organoboron compound from boron trihalide having similar reaction with other p-block halide, example SnCl4. 3 moles of butyl lithium react with boron trichloride to give tributyl boron plus 3 moles of lithium chloride. So this is the figure 3.7 synthesis of organoboron compound from organolithium compound. Lithium alkyl are important catalysts in the synthetic rubber industry for stereospecific polymerization of alkene. Meta derivative of alkyne can react with carbonyl and water to give alcohol. Uses of organolithium compound in rubber industry. Organolithium has advantage over Grignard reagent because Grignard reagent fail to react with highly hindered carbonyl compound, but organolithium react normally with such a compounds. Reaction of organolithium compound at highly hindered reaction sites. So here acetone in presence of lithium uh, tertiary butyl gives alcohol reaction of organolithium compound at high hinder reaction site. Addition with ketene and isocyanate give ketone and amide respectively. So here use of organolithium compound for synthesis of ketone and amide. 3.4 Organometallic compound of magnesium synthesis property structure and bonding uses. 3.4.1 Synthesis of organomagnesium compound. Organomagnesium halides were discovered by French chemist Victor Grignard in 1900. Synthesis of Grignard reagent can be done by reacting magnesium and alkyl halide in ether solvent to form solution of alkyl magnesium halide. Figure 3.11. Ethyl bromide in presence of magnesium and THF give ethyl magnesium bromide. Methyl iodide in presence of magnesium and ethyl alcohol give methyl magnesium iodide. The synthesis of Grignard reagent. 3.4.2 Structure and bonding. Grignard reagent only observed as a dimer. The alkyl magnesium can be observed only in solid state when alkyl is bulky. Example magnesium, carbon, silicon, trimethyl. Grignard reagents are generally solvated, and crystal structure data shows that the magnesium center is typically tetrahedrally sited. For example, ethyl magnesium bromide 2E2O. Example of 5 and 6 coordination have been observed where the macrocyclic ligand impose the higher coordination number on the metal center. Solution of Grignard reagent may contain several species. Example alkyl methium halide, dialkyl methium, magnesium, magnesium halide, dihalide, alkyl magnesium dihalide, magnesium alkyl, which are further complicated by solution. 3.4.3 Reaction and uses of Grignard reagent. It can act as a base to by deprotonating alkaline protons. Propine react with ethyl magnesium bromide in presence of THF at 20 degrees Celsius to form propine, magnesium bromide, and ethane. Basic character of Grignard reagents. Meta derivative of alkyne can be added to carbonyl double bond, which upon hydrolysis gives corresponding alcohol. Then here alkyl magnesium bromide presence of formaldehyde and water give alcohol. Reaction of RMGX methyl alkyl magnesium halide with ketones. Similarly, Grignard reagent gives addition product with the carbon dioxide, which upon hydrolysis gives corresponding acid, magnesium bromide in presence of one carbon dioxide Eth2O and 2 mole, and H3O plus gives CH3COH. Reaction of alkyl magnesium halide with carbon dioxide. Grignard reagent do not react normally with hindered carbonyl compounds. Here, acetone react with in presence of tertiary butyl magnesium bromide water H plus no reaction. Steric hindrance prevent the reaction of bulky alkyl magnesium halide reagent with bulky substrate. Addition to ketene and isocyanate gives ketone and amide respectively. Figure 3.16. Then here reaction with the methyl magnesium iodide in presence of water to give ketones. Then ketene in presence of methyl alkyl magnesium iron and water give ketones. Then isocyanate in presence of methyl magnesium halide and water give amide. 3.5 Organometallic compound or beryllium and calcium. Beryllium, alkyl and alide are made by reaction of organopotassium with beryllium chloride in ether medium. They are hydrolyzed by water and inflame in air. In the vapor phase, dimethylberyllium is monomeric with a linear carbon beryllium carbon unit having beryllium carbon bond distance of 170 picometer. The solid state structure is polymeric. However, bonding in beryllium dichloride can be described in terms of a localized bonding scheme. There are insufficient valence electrons available in dimethyl beryllium for an analog bonding picture. Hence, 3 carbon 2 electron bonds are predicted as described for beryllium dihydride. Figure 3.17. High alkyl are progressively polymerized to a lesser extent, and the tertiary butyl derivative is monomeric under all conditions. Beryllium forms a ferrocene-like sandwich compound with pi electron-rich ligands such as cyclopentadiene. Figure 3.18. Structure of organometallic compounds. N5 and N1 mode of bonding and sandwich type of organoberyllium compound. N1 mode, N5 bond mode. The heavier groups 2 metal are highly electropositive and metal ligand. Bonding is generally considered to be predominantly ionic, while dicycloberyllium and dicyclomagnesium are monomeric and are soluble in hydrocarbon solvent. Dicyclocalcium and dicyclostrontium dicyclobarium are polymeric and are insoluble in ethers and hydrocarbon. 3.6 Summary. This chapter discusses some important concepts to understand the bonding and structure and uses of organometallic compounds of lithium, sodium, magnesium, beryllium, calcium. Synthesis, structure, bonding, and uses of all individual compounds have been discussed.